I am Hitesh Raiyani, Assistant Professor at LJ Institute of Engineering and Technology. This is Class 19, Spherical Cells. The learning outcomes of these lectures is to learn the spherical cells subjected to internal pressure. Also, we will see common examples in this lecture based on the spherical cells subjected to internal pressure. So, let's start our lectures. Now, things spherical cells subjected to internal pressure. So, consider the spherical cells or which subjected to internal pressure P. Here, you can see the intensity of pressure P is applied on the thin spherical cells, and T is the thickness of sphere. Now, let's V is the volume capacity of this cell, P is the intensity of internal pressure, D is the diameter of cell, T is the thickness of cell, and sigma T is the permissible tensile stress for the given material or cell material. Now, as we seen the spherical cell shown in a figure, to design the spherical cell, we have to determine first diameter of cell and second thickness of cell. So first we consider the spherical cells and we calculate the diameter of spherical cell. As this cell is in shape of spherical cell, so we know the capacity of spherical cell, that is the volume of spherical sphere, that is V is equal to 4 by 3 into pi r cube, or you can say in terms of diameter it is pi by 6 into d raised to cube into d cube. Or if you simplify these equations, you get the d is equal to 6v divided by pi raised to 1/3 power. So this is the diameter of cell according to the volume capacities or particular pressure vessel. Now, second things, we have to calculate the thickness of cell. So as shown in a figure here, you can see the pressure intensity is P and thickness of sphere is T. So to calculate the thickness of cell, we have to use the balance equations for the force. So we have to balance the force acting on acting on spherical cell subjected to internal pressure. So here the pressure P is applied, so bursting force is equal to pressure into area. As P is the pressure intensity, so we have to write P in place of pressure, and area which we have to write projected area of pressure. So here you can see the projected area of pressure is the pi by 4 into d square. So these are the equations and gives equation 1. Now, as the pressure is applied on spherical cell, in opposite direction there will be the resisting force is generated. So, and the resisting force of the cell is, so here the resisting force is generated and the resisting area in this spherical cell is shown by the hash. So whatever the hash area, that is the resisting area, and we have to calculate the resisting force when we apply the pressure or P on spherical cell. So resisting force is equal to stress into resisting area. So here we have to consider stress is what? Permissible stress, that is sigma T, and resisting area. Here the hash portion shows the resisting area. So resisting area is nothing but the pi d into T. So if we place the value of stress and resisting area, we get resisting force of cell is equal to sigma T into pi into d into T. So this is the resisting force, gives the equation number 2. As we learned in previous lectures also, we have to balance, we have to equate these two equations, because these two equations is the force equations, and both force are equal and in opposite directions. So we have to equivalent these two costs to get the thickness of spherical cell. Now, so from equations 1 and 2. So from equations 1 and 2 we have, so if we equivalent equations 1 and 2, we get P into pi by 4 d square is equal to sigma t into pi into d into t. So this is the generalized equations when we equivalent these equations from equation 1 and 2. Now we have to calculate the thickness of spherical cell. So from these two equations we have to simplify these equations, and if we simplify the above equations we get the T is equal to P into D divided by 4 into sigma T. So this is the thickness of spherical cell subjected to internal pressure P. Now in this equation sigma T is the permissible stress of spherical cell material. Now in what happens, sometimes the joint efficiency is given. So if eta is the efficiency of circumferential joint of spherical cell, at that time you have to consider the efficiency, and the thickness equations can be modified as T is equal to P into D divided by 4 into eta into sigma T. So this is the equations of spherical cell when we consider the efficiency of circumferential joint. So these two equations you have to use when you design spherical cell subjected to internal pressure. Now next is the consider one example based on the spherical cell, thin spherical cell subjected to internal pressure. Now we know what is the thickness of spherical cell, what is the equations of thickness of spherical cell and diameters of particular spherical cell. Now consider one example. Example 1. A spherical vessel 3 meter diameter is subjected to an internal pressure of 1.5 Newton per mm square. So here the diameter of spherical cell or vessel is given, that is 3 meter, and internal pressure of 1.5 Newton per mm square is given. So here P is given, that is 1.5 Newton per mm square. Find the thickness of vessels required if the maximum stress is not to exceed 90 megapascal. Here the maximum stress is not to exceed 90 megapascal means what? It is given the permissible stress. And we know the permissible stress, that is sigma T is equal to 90 megapascals. And also take the efficiency of joint as 75%. So here efficiency eta is given. So N is equal to 75%. So first we collect the data according to this problem. So here D is 3 meter, or you can say 3000 mm, P is 1.5 Newton per mm square, sigma T is 90 megapascals, or in terms of Newton per mm square 90 Newton per mm square, N is equal to 75% or is equal to 0.75. So this is the data given, and what we have to find, we have to find the thickness of this spherical cell. So as we know the equations of thickness, so T is P into D divided by 4 into eta into sigma T. So as P is given 1.5, D is 3000 and eta is equal to 4.75, and sigma T is given 90 megapascals or 90 Newton per mm square. So if we place all this value in these equations, we get the thickness of this spherical cell or vessel is 16.7, say the 18 mm. So these are the answer what we want. So according to given problems, the thickness of spherical cell is 18 mm. Now next is changing dimension of a thin spherical cell due to an internal pressure. So as you can say, first consider the nomenclature, that is D is the diameter of cell. T is the thickness of cell, P is the pressure intensity, E is the Young's modulus, and mu is the Poisson's ratio. So as we know, the delta V is the final volume minus original volume. As the pressure vessel is subjected to internal pressure, there may be changing volume of spherical pressure vessel. So delta V is final volume minus original volume. And here the pressure vessel is spherical cell. In spherical cell, you can say the volume of spherical cell is equal to pi by 6 d cube. But so according to that, final volume is pi by 6 into d plus small d raised to power 3. So here the diameter for the final volume is considered d plus delta d. Delta d is the changing diameter. So minus original volume pi by 6 into d cube d. So in these equations, delta d is equal to p into d square divided by 4 d into 1 minus mu. Here is the equation number 1. This equation is derived by the use of Poisson's ratio formula, and delta d is becomes pd square upon 4te into 1 minus mu. Give the equations 1. Now in above equations, if we simplify these equations and neglecting the higher order terms, we get the delta v is equal to pi by d into 3d square into delta d. Here in these equations we neglecting the higher terms order. So delta v becomes pi by 6 into 3d square into delta d. Now if we substituting the delta d value, so here in above equations there are delta d and we have a value of delta d, that is pd square divided by 4te into 1 minus mu. So from equations 1 we have to substituting the delta d value in our above equation. So if we substitute the value of delta d and we simplify this equation, then delta v becomes 3 pi d square divided by 6. So into pd square divided by 4te into 1 minus mu. Further, if we simplify these equations, then delta v becomes delta v becomes pi into pd raised to 4 divided by 8te into 1 minus mu. So this is the changing volume due to the internal pressures. Now consider one worksheet problems, that is the example 2. A seamless spherical cell 900 mm in diameter and 10 mm thick is being filled with a fluid under a pressure until its volume increased by 150 into 10 raised to 3 mm cube. Here a thin seamless spherical cell is given and diameter of this cell is 900 mm and thickness of cell is 10 mm and the cell is filled by the fluid until its volume is increased by 150 into 10 raised to 3 mm cube. So here the delta V is given and calculate the pressure exerted by the fluid on the cell, taking modulus of elasticity for the material of cell as 200 kilonewton per mm square. So E is given and Poisson's ratio you have to take as 0.3. So this is the given problems. Consider as a worksheet problems and do it yourself. We will discuss in next lectures. So in this lectures we learn the thin spherical cell subjected to internal pressures, and also we seen one examples based on the spherical cell subjected to internal pressure. Thank you.